Welcome to Atom Video 1. In this video, we're going to talk about the history of the atom. So first, let's talk about what an atom is. An atom is the smallest particle of an element that retains the properties of that element. So if you were to take an atom, which is really super tiny, and blow it up to be the size of an orange, that would be equivalent to taking an orange and blowing it up to the size of the Earth. So just to try to give you an idea of exactly how tiny an atom is. Let's go through the history of how we know what we do about the atom today. So the history of the atom starts with Aristotle, and he's a famous philosopher. He talks about all the matter and the earth is made up of fire, air, earth, and water, and that if you blend these elements into different proportions, you get pretty much every substance that exists on earth. Then comes Democritus, and he comes up with the idea that there are actually these little tiny particles called atomos. Atomos means indivisible. You should know this word, indivisible. That's kind of an important word. We say it every day in the Pledge of Allegiance, indivisible with liberty and justice for all. And indivisible means that it cannot be divided. So when we say that, or Democritus was saying that an atom is indivisible, it meant that the atom couldn't be broken down into smaller pieces. Democritus also says that atoms, these tiny circles, are homogeneous, which means the same throughout, and pretty much just a solid. The problem was Democritus's ideas were contrary to what Aristotle believed, so nobody really pursued it further. Then about 2,000 years later, Dalton comes along and he continues with the ideas set forth by Democritus and says that he does think atoms are these tiny indestructible particles. He thought that atoms had no internal structure, meaning that he didn't know about protons, neutrons, or electrons. He's saying that atoms are just these tiny spheres. He also said that atoms of the same element are identical. So let's say you had one carbon atom, it'd be identical to another carbon atom. Today we know this is wrong because you could have two different atoms, let's say one atom of carbon with a mass of 12 and one with a mass of 14, which are the same element but that have different masses and different numbers of neutrons. Dalton didn't know about neutrons. He didn't know about subatomic particles at all, and that's not his fault, it just hadn't been discovered yet. So Dalton's ideas are actually wrong because you can have the same element with different amounts of subatomic particles. So after Dalton, which is really just saying the atom is a hard sphere and there's no structure inside, no subatomic particles, comes Thomson. Thomson used a cathode ray tube and he was able to figure out the mass to charge ratio of the atom. He figured out that the mass of a charged particle was less than the mass of hydrogen atom, which was the smallest known element. So there must be subatomic particles or particles inside the atom, therefore the atom is divisible. So let's look at the cathode ray tube. This is Thomson's experiment. We have a positive and negative metal discs. And when you pass an electric current, we make a beam appear to move from the negative to positive end. We see the beam is attracted to the positive plate. That means there has to be something or a subatomic particle which is negative. Hence, he discovered that there is a negative subatomic particle. We know the negative subatomic particle is called the electron. So if here's my atom, his model is called the plum pudding model. Plum pudding was something they ate at the time. Kind of would be like a chocolate chip model, I think, if we talked about it today, where you have negative electrons plopped in a positive sphere. Next comes Rutherford. Rutherford shoots positively charged alpha particles given off by uranium at a sheet of gold foil. And what happened was most of the particles went straight through this sheet of gold foil. And using the fluorescent screen, he was able to see exactly where these particles were bouncing off. But a few of them bounced back. Now, not a lot bounced back. Turns out maybe only one in about 2,000 particles actually repel back. So most of the particles are going straight through. He's able to figure out that if some of the particles are going to deflect, that means that the nucleus is positive because he was shooting alpha particles. They had the same charge, that's why they repelled each other. He's also able to figure out that most of the atom was empty space because most of the particles are going straight through. So Rutherford's experiment is important for two reasons. First, it tells us that the atom is mostly empty space. Secondly, it tells us that there's a positive nucleus in the atom. It's really small because you don't hit it too often, only about 1 in 2,000 times. But when you do hit it, whatever the charge is, it has to be positive because the charges are repelling the charges of the alpha particles, which are positive. So in summary, Rutherford's experiment These are the things that we need to know because Rutherford is asked about pretty much on every Regents exam. We need to know what was Rutherford doing? Shooting alpha particles at a sheet of gold foil. What happened? Most of the atoms went straight through the atom. So we need to know why did they go through the atom? They went through the atom because the atom is mostly empty space. We also need to know that some of the particles deflected. Why did those particles deflect? They deflected because the alpha particles are positive and the nucleus is positive and like charges repel each other. So from his experiment, we learned the atom is mostly empty space, and there's a little tiny dense positive center that we now call the nucleus. Following Rutherford's model comes the Bohr model or the planetary model, where you have electrons located in rings or orbits. We'll talk about Bohr's model and the final model of the atom, the model in a later video.